This is a problem from the 6.1 homework that I was emailed about. 6.1, this is question 2. I started to write out a solution and got halfway through the problem and realized this might require a little explanation to go along with the solution. I don't have my headset microphone with me. I'm just in my office kind of shouting at my laptop. So I hope that you can hear me okay. Feel free to email me if there's something you can't hear you'd like further explanation on. All right, in this problem, the region here is being rotated about the y-axis. And the other thing is I have to get reacquainted with my writing tablet every semester, so I hope that everything comes out legible enough. And I'll apologize in advance for my handwriting. Okay, so back to this problem. We're rotating the region about the y-axis. Now, first thing, in 6.1, you're using either the disk method or the washer method, depending on your region. But either way, in 6.1, you always want the typical rectangle perpendicular to the axis of rotation. So when you're revolving about the y-axis there, then the typical rectangle should be perpendicular, which is why they have this line, this red line, drawn in the graph. They're indicating where the typical rectangle would lie. And see, there's the problem with my handwriting right there. All right, so first thing would be to draw your typical rectangle somewhere in the region. Now notice that if that rectangle, let me do a little diagram off to the side here. If that rectangle there is revolved about the y-axis, that's going to result in a solid disk. There's no hole in the middle. And so the reason I bring that up is we know now that we're using the disk method as opposed to the washer method. The other thing I'd like to point out before I go any further is once you set up your rectangle, when you have horizontal rectangles like this, then you're talking about an integral in terms of y. And the way I always explain that is dx or dy is going to be the thickness of the rectangle. In this case, the thickness lies along the y-axis, so it's an increment in y values and not in x values. So that thickness is dy, which means that everything needs to be written in terms of y in this problem. So from here on out, whatever we write, we're looking at y values and not x values. Okay, so in the disk method, your formula is the volume of that solid of revolution is going to be pi times the integral from a to b. Let me not specify the limits of integration for now. Times the radius squared times the thickness of the disk. Okay, in this case I just talked about how the thickness of the disk in this problem is going to be dy. The width of that typical rectangle is an increment in y values. So dy for the thickness. Now, radius can be tricky. So looking at the disk over here, you can see that the radius is just, it's sort of the height of this rectangle right here. So this, my writing tablet isn't working well. This right here would be your radius, and it needs to be written in terms of y. So I'm writing r of y, so that radius should be a function of y. And in this case, well, here, let's think about it in terms of height of the rectangle. So over here, x equals 0. If you're right on top of the y-axis, then x equals, here we go, 0. Over here, you have the curve for the function x equals 4 tangent pi over 4y. So over here, x equals that quantity, 4 tangent pi over 4y. So the difference in those x values is our radius. You can kind of think of it as the larger x minus the smaller x. So 4 tangent of pi over 4y minus the lower x over here is 0, so minus 0, which you don't even really need to write. So the radius in this problem is 4 tangent of pi over 4y. And we want that entire quantity here squared, radius squared. set this up. So volume equals pi times. Now the one thing that I haven't talked about are the limits of integration. And like I said, everything is in terms of y. So we're going to integrate from where y equals 0 to up here. This will be our upper limit, the upper edge of the region, which is where y equals 1. So our limits of integration are 0 to 1. All right, so now we have the integral set up, which is actually half the battle right there. But now you have to evaluate the integral. So the first thing I'll do is, well, I'm just going to square the quantity in parentheses. So that gives me 16 tangent squared. Make sure that you square each part of pi over 4y dy. And the 16 isn't really helping me here, and that's just a constant coefficient, so we can move that out front. So I'm going to write this as 16 pi integral from 0 to 1 of tangent squared pi over 4, I'm sorry for my handwriting, y. And now this is where I decided, okay, I need to make a video to explain this problem, because there's another complication now. We're not prepared to integrate tangent squared just by itself. We don't immediately know a function whose derivative is tangent squared of pi over 4y. So we need to rewrite this tangent squared. So you have to go back and think about trig identities. And the one that comes in handy here, let me see if I can switch colors. And I'm sorry, my printer is rumbling for no reason. The trig identity that comes in handy here is this one. 1 plus tangent squared theta equals secant squared theta. And that trig identity is going to come up again and again in calculus too. So that's one that's worth going ahead and memorizing. Now that's not exactly what we're going to use here. If I isolate the tangent squared, since that tangent squared is what appears in this integral, you have tangent squared theta equals secant squared theta minus 1. This is what we're going to use. So I'm going to change the tangent squared expression to secant squared minus 1. So I'm going to rewrite this as secant squared. Now I have to keep the same argument, pi over 4. Argument is just the word for what's inside of your trig function, minus 1. Okay, let me switch back to black. Okay, so I'm just jotting down the rest of the integral here. And again, I hope you can read my handwriting. Okay, and now I'm going to look at this as two separate integrals. I'm going to break this up. So 16 pi, I'm going to leave that out front, and I'm going to set up a brackets because I'm going to write two separate integrals. Integral from 0 to 1 of secant squared pi over 4y dy minus the integral from 0 to 1 of 1 dy. Slide this up. Okay, and I'm going to evaluate these integrals one at a time just to maybe make this seem a bit simpler because there is a lot going on at this point in this problem. So let me come way over here and look at just integral number 1. So, oops, I lost my, I'm hopping around the screen here. Just the integral from 0 to 1 of secant squared pi over 4y dy. And so now, I said a second ago, we don't know a function immediately whose derivative is tangent squared pi over 4y. And that's what you're really doing when you solve integrals, or when you evaluate integrals. You're looking for a function whose derivative is whatever you have in the integrand. Now, secant squared is a different story. And it's helpful in calculus too if immediately when you see secant squared, you think that's the derivative of tangent. So we do know a function whose derivative is secant squared. Now, the pi over 4y throws a little something extra into the problem once again. So to deal with that, we should actually use a u substitution. Okay, so I'm going to let u in this integral equal pi over 4y. Then du is just the constant pi over 4. Here you have a constant times y, so the derivative is just the constant pi over 4, and then derivative of y, we'll just write dy. Okay, so notice if you look back up here, we have just dy. We don't have that pi over 4. But I'm just going to squeeze in that multiple pi over 4 just to, so this video doesn't go on for 20 minutes. I'm just going to squeeze it in on this step and then put the reciprocal 4 over pi out front. Now this way, I've really only multiplied this integral by 1 because it's really 4 pi over 4 pi if you look at the product of 4 over pi and pi over 4. So I haven't actually changed the integral. But now, when I write it this way, I can see that, all right, that's du, pi over 4 dy, and then here I have u. So I could rewrite this integral. I'm going to switch back to black here. I can rewrite this as 4 over pi. Let me just put little asterisks for the limits of integration. I'm not going to worry about those guys right now. Secant squared of u du. Secant squared of pi over 4y, that's u, times pi over 4 dy is du. Now, like I said, we know a function whose derivative is secant squared u. That's tangent of u. So that's the antiderivative in terms of u. Okay, and this was a definite integral, so I'm putting little asterisks for the limits of integration. I don't want to worry about them right now. I didn't want to bother converting them, so that now I can write bracket here. 4 over pi. The antiderivative is tangent of u, which recall that u is equal to pi over 4y. So tangent of u is equal to tangent of pi over 4y. And that's evaluated from 0 to 1. Now that I've plugged the 1 back in, now I'm putting the 0 and the 1 back in too. Those are our limits of integration in terms of y. So now I can just substitute tangent of pi over 4 times 1, which is pi over 4, minus tangent of pi over 4 times 0 is 0. This gives me 4 over pi. Tangent of pi over 4 is 1, and tangent of 0 is 0. So actually, this gives me just 4 over pi. So this integral number 1 is equal to 4 over pi. Integral number 2, I don't think that you really need me to show you how to do that one. And so I'm hoping this will actually get you to the correct answer to this problem. I'm arguing with myself right now about whether I should finish this one up or not. But I'd like to go ahead and finish it so that you can verify that you have the correct answer. So the antiderivative of 1 with respect to y is just y. And then I plug in 1, so I get 1, minus plug in 0, I get 0. So integral number 2 has a value of 1. So if I go back up here, and I'm going to have to, this is going to look a bit sloppy here, but I'm going to draw an arrow down here. Then for the volume, I now have 16 pi times integral number 1 gave me this value, 4 over pi. 4 over pi minus integral 2 gave me the value 1. That's over here. Integral number 2 gave me the value 1. And I'm not sure, I'll have to look into MyMathLab about how exactly they accept your answer. I would think that they would accept it in this form, but you could also distribute